Hey everybody, Mr. Piercy here. What we're going to be taking a look at in this video is how to find the surface area and volume of spheres. So spheres are one of those things in geometry that everybody can probably identify what they are visually. If I gave you a bunch of objects and said identify the ones that are spheres and not spheres, everybody would be able to do it because they know it looks like a ball. The definition of a sphere, however, some people would be very hard pressed to give an accurate definition of what a sphere is. Very similar to if I asked for the accurate definition of a circle. Again, students would be very hard pressed to really give a proper definition of it sometimes. Well, the area of this, or the definition of a circle is a set of all points in a plane that are equidistant from a given point. So it makes sense that since if a sphere is essentially just kind of like a revolving circle, so to speak, if you spin it fast enough around a given point, it'll take the shape of a sphere. The definition of a sphere would be the set of all points in space that are the same distance away from a fixed point. And spheres have a lot of the same parts that circles do. They have a center, a radius, a diameter. Instead of a semicircle, if I cut a sphere in half, I have a hemisphere. We can have tangents inside of spheres, just like we can have tangents inside of or outside of spheres, just like we can have tangents outside of circles. We can have chords, secants, all that stuff that circles have. But the primary ones that we're going to be looking at would simply be the radius and the diameter. Now, the sphere itself can have a circumference, just like any other circle would. But one of the things that we're talking about here that you probably have seen, you're like, what's a great circle? Well, a great circle essentially is a circle that goes around the entire circumference of the circle. So the diagram that I'm giving you here with a kind of like a globe, latitude and longitude. Well, every line of longitude, because they're going to go through the poles of the globe or the poles of the Earth, every line of longitude would be considered a great circle because it goes around the entire thing. It goes around the entire circumference of the circle. But you can kind of see here with the lines of latitude, not all of the lines of latitude produce circles that are of the same size. So the only line of latitude that would be considered a great circle would be wherever the equator is located. Um, but this is great circles are going to really get into the idea of things where we talk about non-Euclidean geometry. There's some basic uh, non-Euclidean geometries that we kind of identify or that we study a little bit when it's necessary. And we have, oops, I can't spell. We do have something called spherical geometry, which is the geometry on the surface of a sphere. It is possible to do certain things in spherical geometry that we can't normally do in Euclidean geometry. And of course, Euclidean geometry is the type of geometry that most people typically think of as geometry. That's what you study in pretty much all of your high school math geometry kind of classes. Well, it is possible to, because of the way things curve on the surface of a sphere, it's possible to have a triangle that's less, where the three angles inside of a triangle would be less than 380. It would be less than 300. I can't say. A triangle that would be less than 180 degrees. I'm sure you know what I meant to say. I'm trying to talk and write at the same time, and apparently that's too much for my brain. This right here that I've kind of outline with the two lines of longitude, that is actually a polygon in spherical geometry. In Euclidean geometry, the smallest or the polygon with the fewest number of sides is a triangle. It has to have three because I have to have a closed shape that's made up of lines in order to have a polygon in Euclidean geometry. Well, in spherical geometry, the lines are those great circles, or the circles that go around the sphere itself, and it still has the same basic definition. It is a closed figure made up of lines of, but in this case, again, the lines are curved. So the smallest number of sides that it takes, or the fewest number of sides, I should say, rather, to create a polygon in spherical geometry is a two sides, and that would be called a lune. And it's called that because it kind of looks like a crescent moon shape. Um, But there's a whole bunch of stuff about spherical geometry, but since I had that stuff there, I figured I'd go ahead and talk about it. Well, we're not going to really get into too much of it, but hopefully by now you've had the time to get the definitions copied down, but let's move on. Surface area of a sphere. What I'm going to try and do here, for those of you that are watching the video, I'm going to try and include a link here because I typically try to say anytime that you use a formula, especially all the stuff that we do in geometry, you should know where the formula comes from. Well, it turns out that the formulas for area and surface area and volume are fairly intuitive and easy to explain and or do little experiments over. Surface area of a sphere is 4 pi r squared, and to try to explain to you where the formula comes from is not an easy process. So what I'm going to try and do is in the video here, I'm going to try and add a link to another video. It's about 10 minutes long that walks you through a pretty straightforward, it's about as basic of an explanation that you can get, and it's still going to take about 10 minutes to explain where that equation comes from. And it's a geometry approach. It's not any kind of weird calculus stuff. There's calculus methods where you can use integrals to determine what the surface area of a sphere is, or to prove that the surface area of a sphere is this equation, 4 pi r squared. But that's the equation, 4 pi r squared. I'm going to try and add a video link here to this. So that way, if you're very curious, you can watch it and see where the formula comes from, and understand it's not the easiest thing for me to try and explain or just draw out quickly. But 4 pi r squared, let's just see how we can use it now. Here I have a sphere where I know that the radius is 7 centimeters. Now, not always will the radius be given to you. Sometimes they'll give you the circumference of the diameter, or the circumference of the sphere, rather, and you can kind of go backwards to find out what the radius is. Maybe they, again, give you the diameter, but either way, we need the radius. That's really the only dimension that we care about for spheres, because there's no planes, there's no faces that we can sit, or no polygons that we're going to be trying to find areas or anything like that of, no circular bases, nothing. We only care about the radius, and the radius is going to be the same throughout the entire sphere. So that's, again, the only dimension that we really care about. So substituting the radius of 7 into the equation gives us 4 pi times 7 squared. So 49, which is 7 squared, 49 times 4 gives me an exact surface area of 196 pi centimeters squared, and the approximate value would be about 615.8 centimeters squared. Okay, but that's a fairly straightforward exercise as far as finding the surface area of a sphere when you're given the radius. Here, it's telling you that the surface area of a sphere is 110.25 pi feet squared, and we want to know what the diameter is. Well, of course, the diameter is double the radius, so we can use the surface area formula to find the radius and then double it. So substitute the surface area that there was given to you, 110.25 pi. What I'm going to do is divide both sides by I'm going to divide both sides by 4 pi. Now, when I divide the 110.25 pi, if you have that in your calculator, make sure when you divide by 4 pi, put the 4 pi in parentheses. The pi is not necessary in the calculator. You can just say the 110.25 divided by 4, because the pi in the numerator and the denominator are going to just simplify to be 1. But either way, we get about 27.6 for the radius squared. And of course, I take the square root of both sides to get the value of the radius. So the radius is about 5¼ feet. So since the diameter is double that, I double the 5¼ and say the diameter of the sphere is about 10½ feet. Now we're getting into volume. And again, here I'm going to try and add a link to a separate video because, again, volume is not a very intuitive thing. It's not a very easy thing to try and demonstrate. In class, what I would try to do is I could have a sphere that has a radius that is congruent to, say, the radius and height of a, you know, of a similar sized cylinder, and we could kind of demonstrate that it would take, or a similar sized cone, and we could show that it would take 4 cones of a radius and height that are congruent to the radius of a sphere. But again, it's not the easiest thing to try and demonstrate. I can't really just write it out very quickly and say, oh, this is where it comes from. So I'm going to add a video description link here to another video that will again give you a geometry perspective of showing you where this volume formula comes from. But 4/3 pi r cubed is the volume of the sphere. And for now, we're going to just go ahead and try using it and see what we come up with. Now, again, starting off, it's a very kind of straightforward approach. We have the volume is 4/3 pi r cubed. We're given the volume, or we're given the radius to be 3, so I substitute 3 here. And then I want to simplify it. Now, here we go. This is the one I added some extra stuff to. They're kind of skipping some steps here, I think. 4/3 pi r cubed. How do we go from that to the approximate volume of 113.1, basically? Well, what we're doing is we're saying 3 cubed. Well, 3 cubed is 27. And here, what I'm doing is, let me pick a color that will contrast with the red. Here, this 3 goes into that 27 9 times. And that's where I come up with volume is equal to 4 pi times 9. And then the 4 times 9 is just 36 pi millimeters cubed. So here is, of course, the exact answer. And the 113.1 would be the approximate volume of the sphere. So here is a good example, and we've seen this with other volume things, with pyramids and prisms and cones and cylinders, where we have a composite shape. Here I have a cylinder where I'm removing a hemisphere. I'm taking part of the half of a sphere out of that cylinder. So what I'm going to do here is I'm going to say, well, whatever the volume of the cylinder is, because that's the overall shape, if I take out the volume of a hemisphere, whatever's left is the volume of the shape that I'm provided. So the volume of the cylinder is pi r squared times height. The volume of a hemisphere will be half of the sphere formula, so 1/2 times 4/3 pi r cubed. So substituting here, I'm going to wind up substituting a 3 for the radius, a 5 for the height of the cylinder, and again a 3 for the radius of the sphere. Sorry for the pause there. Again, I think I added, there it is, I added some extra stuff that I thought that they were missing. So the 3 squared gives me 9, and here specifically what I'm doing is I'm combining my fractions. I'm multiplying my fractions together. The 1/4 times the 4/3, that would give me 4/6, because remember, when we multiply fractions, that's no problem. Top times the top, bottom times the bottom. So 1 times 4 is 4, and 2 times 3 is 6, so that gives me a fraction of 4/6, and 4/6 simplifies to be 2/3. And again, of course, I can simplify the 3 and the 27 to be 9 times 2, which will be 18 pi, and that's what I'm getting here. Okay, so 45 pi minus 18 pi, that is the exact answer of 27 pi inches cubed, or about 84.8 inches cubed for the approximate volume. So at this point, we're kind of coming to the end of the lesson. We've talked about how you use surface area formula, how you use volume formula for a sphere. At this point, let's go ahead and pause the video and work out these 2 problems. And when you're done, hit play and check your answers as how they compare to mine. Okay, so we're given the, for problem number 1, we're given the diameter of a sphere. So it's giving us as a funky number, 1 divided by the square root of pi, as the diameter. Well, I have to take I have to know what is the radius. So the radius is half of the diameter, so I multiply the diameter that was given to me by 1/2, and I say the radius is 1 over 2 radical pi, or 1 over the 2 times the square, excuse me, times the square root of pi. So that's the radius of the sphere. Now I'm going to substitute that into the equation, and 4 times the radius, 4 pi times the radius squared gives me 4 pi times 1 over 2 radical pi squared. When I square the fraction, the exponent of the 2 gets used to the numerator and to the denominator. So what's going on is properties of exponents is going to say, well, the fraction squared says 1 squared over 2 squared times radical pi squared. Well, the 2 squared gives me that 4, and if I square something that I'm taking the square root of some already, so the square root of pi squared is just pi. And so at that point here, let me pick another color that will kind of contrast with the blue. So let's go green. So here, 4 over 4 simplifies to be 1, pi over pi simplifies to be 1. So I'm just left with 1 divided by 1, which is just 1 meter squared. So that's the surface area. So the next one, the surface area of a sphere is given to you to be 169 pi. Find the radius again, so we're going to kind of work backwards on this one. Substitute the surface area of 169 pi, divide both sides by 4 pi, and I get 42 and a quarter for the radius. Take the square root of that, and okay, well, thank you for that pop-up about my YouTube watching practices. But anyway, the radius is about 6.5 inches. So now at this point, again, go ahead and pause the video and answer these last 2 questions if you haven't already done so. And when you're ready, go ahead and hit play and compare your answers and work with mine. All right, so hopefully we have good answers. If you've already done them, great. If you needed to take the time to work them out again, I don't know. But anyway, number 3, the radius of a sphere is given you to be 2.4 centimeters. Find the volume of the sphere. Round your answer to 2 decimal places. I actually don't think I did 2 decimal places. There we go. So here the volume, 4/3 pi r cubed. Substituting the radius of 2.4, we're going to cube it. Now here, the 13.824, that doesn't simplify with the 3 in the denominator very nicely. So if I multiply the 4/3 to the 13.824, I get 18.432 pi centimeters cubed. And I don't want to round that because I don't round numbers if I'm giving it as an exact number. Really, if I did it to 2 decimal places like the instruction said, I should have said 47.91 centimeters cubed. But anyway, that's the volume of the sphere that we would have. And the last one here, it's kind of going in the opposite direction of what the example problem in the notes gave us. Here, instead of subtracting a hemisphere from a cylinder, now we're adding a hemisphere to a cylinder. So if the radius is 5.8 feet and the height of the cylinder is 14 feet, we're going to say take a cylinder, add a hemisphere to it in this case. And so substituting, I get 5.8 squared and 14 for the height of the cylinder. 1/2 times 4/3 simplifies to be 2/3, and of course the radius 5.8 cubed. So here, this one is not a very nice number at all. 470.96 pi plus the 390.224 pi over 3, that is the exact volume, but that's really not a nice number. And if I try to get a common denominator with a 3, I really wind up with an ugly, ugly number. So I'm going to just go with the volume here. Again, I wasn't really paying attention to the instructions. I didn't round it to 2 decimal places. I went to 3 like I normally do for pre-AP math. And the volume is about 1888.2 cubic feet. But that's it for volume and surface area of spheres. Remember the volume formula, 4/3 pi r cubed. Surface area formula is 4 pi r squared. If you haven't taken a look at the links for the additional videos, if I was able to manage to do it, I'm not the most I make these videos, but I'm really not super awesome at editing them yet. But anyway, hopefully you took the time to watch the videos, or at the very least look something up yourself that didn't require calculus to find equation for surface area of a sphere, and that's about it. Remember, if you have any questions about anything that you've seen, email me, send me a comment, anything, come see me in class, and I'll be happy to help you guys out. But until next time, guys, thanks for watching. Be good and take care.